Hello, this is part 6 of the impulse momentum videos. Today I'm going to talk about a glancing collision, which is also elastic. Glancing and elastic collision. Now these are two-dimensional problems. This could be a surface like a billiard pool table, and you have two billiard balls, maybe, excuse me, approaching each other, or one of them is stationary and the other one is about to hit it, like this. Let's say MA is the mass, and here's another one. The second ball with a mass MB. Now, let's say MA is initially moving along this direction here, like that. And let's draw a velocity vector, an arrow that represents the initial velocity of A. So in our notation, this will be VA or VA1. One means before the collision. Okay? So right now, everything is one-dimensional. Okay? Just movement along one direction. But once the collision occurs, because B is a little offset to that line, there will be a velocity vector for MB and also MA, which is not along the original line. So this will be here, that original direction, but now A is probably moving vertically like this, and then not vertically, but some at an angle, and MB similarly. So let's pick different color, blue, and some, I don't know, here, such, or like that. Okay, so this is VA2, and this is VB2. So I assume that VB1 is 0. You don't have to. I mean, you can keep it general. You can give the initial velocity to B as well. Doesn't matter. The method is important here, how you're going to solve this problem. So we have these angles here. Call it theta. Another angle below that line, which is phi. Okay, so theta and phi are both positive angles. Sometimes in some books you'll see phi as a negative number because below the x. Doesn't matter. I mean, here's how I define it. So the problem is then finding these velocities. Okay, it's a glancing collision and also elastic. So momentum conservation is still valid. I'm just going to write it down. P total before is always valid, equal to the total momentum after the collision. Okay, and the elastic part, it has to do with kinetic energy conservation. Kinetic energy conservation, which is, let me just write it here, the total kinetic energy before, that would be for this example, 1/2 MA VA1 squared. There's no contribution from the second guy. It's not moving. But after the collision, that one starts moving too. The total kinetic energy will be 1/2 ma va2 squared plus 1/2 mb vb2 squared. Okay. So these are billiard balls, so probably the masses are the same, right? So let's just call this M. M is MA and MB. They're equal. All right. So this energy equation can be simplified to, after getting rid of 1/2s, and m's are the same, so what is left is VA1 squared is equal to VA2 squared plus VB2 squared. Okay, so we'll need this. Let's keep it there. Let me just box it here. I'm going to be using it later. Let's go back to the momentum again, momentum conservation. Now, P before is equal to P after. What is P? Total momentum. MA VA1 plus MB VB1 equal to MA VA2 plus MB VB2. Now for this problem, M's are the same. Okay, we can get rid of the masses. And also VB1 is 0, remember? So this will simplify to VA1 equal to VA2 plus VB2. Okay, it is a vector equation, and these two vectors, VA2 and VB2, happen to be, when added, gives you VA1. So right there, this was VA2, right? And here VB2. If you add them up, you get the original velocity of A. VA2 and VB2. This is theta, and this is phi. All right, so it is a vector equation, which means actually it is two equations in one, all right? Now, if you write this in terms of components, let's do it over here in terms of, let's say, the x component. If this is the x direction here, and this will be y. Along the x direction, VA1 is the only component, so I'm just going to write here VA1. VB1 is 0. VA2, now the x component of VA2, that will be VA2 cosine theta. And VB2 will contribute to the x component as well, plus VB2 cosine phi. Now along the y direction, actually there is nothing in the beginning. Before the collision, this is before, this is after. Before the collision, there is no momentum component in that direction. There is no velocity component either, so just 0. And after the collision, we have y components. So VA2 sine theta, and VB2 will have a negative component. Okay, I'm using sine, well, phi is positive, but the y component points in the negative direction. Therefore, VB2 sine phi. Okay, so I have 3 equations, okay? One in the above, like this one, from energy, and these 2 from momentum. So let's see what we can do with these. Now, in the second and third equations, I have VB2 cosine phi and sine phi. Now, why don't I multiply the first equation by, let's say, sine phi. And then I can multiply this by cosine phi, everything here, and then add these equations, and then get rid of the B2 term. Let's try it. So, VA1 sine phi equals VA2 cosine theta sine phi plus VB2 cosine phi and sine phi. And the second equation, I'll have 0 here. VA2 sine theta cosine phi minus VB2 sine phi and cosine phi. Now if I add these, I'll get here VA1 sine phi. These 2 terms are the same, so I get rid of those. Now factor the VA2, and that's cosine theta sine phi plus sine theta cosine phi, which is the sine of theta plus phi. So I use that trigonometric identity there. Okay, theta plus phi. All right. Now, what else could I do with these 2? Now, what if I multiply the first equation by, I have cosine phi. What about I multiply it by cosine phi? Cosine phi, and multiply this one by maybe negative sine phi. Okay. Now, if I do that, I'll have here VA1 cosine phi equals VA2 cosine theta cosine phi plus VB2 cosine squared phi. And here, this time 0 is 0. And then VA2 sine theta times negative sine phi. So put a negative here times sine phi. There's a negative here. 2 negatives make positive. So VB2 sine squared phi. Now if I add these two, on the left I will have VA1 cosine phi. Okay? On the right hand side, now I can factor VA2. Then this will read here cosine theta cosine phi minus sine theta sine phi plus, and if I factor VB2 here, cosine squared phi plus sine squared phi, which is what? 1. And this thing here is cosine theta plus phi. All right. Now, I'll need this equation and the one before. Now, both have sine theta plus phi, and the other one has cosine theta plus phi. So on the left-hand side, I have sine phi and cosine phi. So why don't I do this trick one more time? All right. Meaning, let me see. Take the square, huh? So I will need the square from the energy equation anyways. So VA1, okay, I'm going to move here now. VA1 cosine phi. This squared will be equal to VA2 squared times cosine theta plus phi squared plus VB2 squared plus 2VB2 times VA2 cosine theta plus phi. Okay, so let me draw a line here. All right, so I just squared this term, and over there I have this for VA1 sine phi. Let me square that as well. Let's switch to black, color black. There we go. So over there I will have, from the first equation, VA1 sine phi squared, and that will be equal to VA2 squared times sine theta plus phi squared. All right. Now, if I add these two together, hopefully we're getting there now. So VA1 squared plus cosine squared plus sine squared, which is 1. All right, I'm not writing it. Now equals. Now you factor VA2 squared. And what is left? Cosine squared plus sine squared. Again, 1. Plus VB2 squared from here, plus this term, 2VB2 and VA2 cosine theta plus phi. Okay, so what we got here has an extra term. The extra term is this guy here. if you compare this equation with the energy equation from the beginning, this is extra. So we got to get rid of it, okay? We don't want it. That has to be 0. That term has to be 0. Well, we know VB2 and VA2 are not 0. So what is 0? This is 0. Cosine theta plus phi is 0, which means this has to be 90 degrees. All right, so it turns out that if the collision is glancing and elastic and the masses are the same, then the angle between the two after velocities will be 90 degrees. This will not happen if the masses are not the same, then we won't be able to get rid of them, okay? So we have to solve the equations, you know. I mean, you may have the initial velocities, final velocities. If you know the final speeds, you can find the angles, or you can find, I mean, depending on the number of unknowns and the given. Usually, you can solve this problem without even referring to the energy equation. It is possible because you're going to be left with 2 equations. From the momentum, you have one in the x direction and one in the y direction. If the number of unknowns are 2, it could be one of the speeds and the other angle or something like that. You can still solve it, okay? And then you can check, hey, was this an elastic collision or inelastic? What would you do? You want to find the before and after kinetic energies and then compare them. If those kinetic energies are the same, you may say, okay, they were elastic, okay? Or sometimes the problem will be such that maybe the masses are even equal. You'll find out that they happen to be perpendicular to each other, okay? Which shouldn't come as a surprise now, because now you know why they have to be perpendicular to each other. Okay, so the 2 vectors here and there. Okay, these were the velocities after the collision. VA2 and VB2. These will be perpendicular if it is elastic and m's are the same. If they're not the same, then you should be given what they are, because you're going to need them in the equations. All right, I'm going to stop now.